Good day, and welcome to our webinar on troubleshooting techniques for AC induction motors, brought to you by CFE Media and Technology and sponsored by Aegis, LAP, Radwell, and Parvalux. Joining us today will be Michael Lyda, Motor and Drive Engineer, and Ronnie Elford, Motor Lab Coordinator, both with Advanced Energy Corporation. I'm Kevin Parker, editor of Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted on CFE Media websites with the on-demand version of the webcast. The exam is for one RECEP ASIC Certified Professional Development Hour. To get the best results from the webcast platform, please make note of the following. For technical problems, click on the question mark at the top right-hand corner of the screen to bring up a list of system checks to make before escalating to an online technician. If you experience issues with the slides or audio, please refresh the browser or click the Refresh Media button directly under the presenter's headshot. Volume settings can be controlled by adjusting the volume on your computer or by adjusting volume on the platform. If a technician is needed, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to technical questions will be in the Answered Questions box on the left-hand side of the screen. The Ask a Question box is also used to ask the speakers questions. Ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides, use the Event Resources box on the left-hand side of the screen. You can download the presentation until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. We'll now hear from the sponsors of today's webinar. At the end of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Stay tuned for today's presentation and discussion.
VFDs can save 30% or more in energy costs, but VFDs can damage motor bearings. Without shaft grounding, VFD-induced voltages can discharge through motor bearings, causing damage such as pitting, frosting, and fluting, and unplanned motor failure in as little as 3 months. Aegis shaft grounding rings provide proven long-term protection against VFD-induced bearing damage. By channeling harmful shaft currents away from bearings and safely to ground, Aegis rings ensure that motors last for the full L10 life of their bearings. And while you can install Aegis rings yourself or have a motor repair shop install them, the easiest way to protect your motors is to purchase them with Aegis rings factory installed from any of a growing number of motor manufacturers. To protect VFD motors, always specify Aegis rings. To learn more, visit the Aegis website and schedule a lunch and learn worth 1 hour of professional development.
We came to this product because a customer in the US touched base with us looking for a UL TCR rated servo cable, which can be also used in continuous flex applications. The idea was that we just have one cable for the whole installation of the servo motor and drive application, not worrying about any cable track or cable tray portion of it. The benefit for the customer is pretty obvious in this case. The customer just needs one cable where he used to have to use two cables in the past. And with that one cable, he doesn't need to have an interconnection between a tray-rated cable and a continuous flex cable at the machine level. The challenge in this project was that first we had to find proper materials and compounds. Then we had to create a design which fulfills both tray-rated cable and continuous flex cable design rules.
Hi, I'm here to tell you about FANUC part number A06B0032B575. This FANUC motor is a 176 volt, 2.8 amp. This runs off the BM series amplifiers. It is primarily used for CNC machines. Thanks for watching.
We have this product in stock and ready to order today. Visit us at radwell.com to place your order.
Welcome back. In addition, the webinar is sponsored by Parvolux Electrical Motors. Parvolux Electric Motors is a leading global manufacturer of geared motor solutions chosen by manufacturers to power hundreds of diverse applications. From industrial cleaning equipment to materials handling equipment, Parvolux provides the reliable power for a range of workplace applications. Their team of application engineers will work to meet any requirement, including fully customized solutions. For more information, go to parvolux.com. I'd now like to introduce today's speakers. Ronnie Alford joined Advanced Energy in November 2018, having spent the past 2 decades with the electrical equipment company in various roles in the electrical distribution and motor repair business of the company. Ronnie was involved in field service work, electrical maintenance, and testing, with significant training and professional certifications in these areas. He is currently involved in conducting motor systems testing, implementing lab improvements, maintaining calibration certifications, and training. Ronnie received his associate degree in HVAC and refrigeration engineering technology from Wake Technical Community College in 2001. Ronnie is also an approved auditor for the EASA accreditation program for third-party quality motor repair. Michael Lyda started working for the Advanced Energy Motor Lab in January 2010 as a co-op student. After completing an engineering fellowship with Advanced Energy, Michael moved into the Motor Lab Coordinator role in June of 2013. With extensive testing experience in the lab, Michael moved into the Laboratory Director role in August of 2019. He is involved in motor system testing development, research, and training on a wide range of applications to meet the needs of Advanced Energy's customers. Michael received his bachelor's degree in electrical and computer engineering and minor in mathematics from North Carolina State University. Michael is also a member of the Advanced Energy commercial and industrial team, participating in energy assessments and recommending energy conservation measures at regional facilities. Michael, welcome to today's webinar, and please go ahead.
Thanks, Kevin. Thanks, Kevin. And I will add, if there are any issues with audio, just list those in the Q&A portion of your screen, and these folks will deal with that. On behalf of Ronnie and myself, I would like to thank Kevin and the team at CFE Media for giving us the opportunity to present this topic today. I would like to start with a brief background and description of Advanced Energy, and then we'll get into the presentation. Advanced Energy was founded in 1980 by the North Carolina Utilities Commission to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. We are an independent, nonprofit corporation governed by a board of directors appointed by the Governor of North Carolina and member utilities. We continue to work with our member utilities on energy efficiency and conservation projects to this day. Our current North Carolina member utilities include Duke Energy, Dominion North Carolina Power, and North Carolina Electric Membership Corporation. In addition to creating means for sustainable, energy-efficient economic development for the ratepayers of North Carolina, Advanced Energy also operates as a fee-for-service consultant to clients nationally and internationally. We work with electric utilities, governments, and a wide variety of private organizations in 5 targeted areas, including residential, commercial and industrial, solar, motors and drives, and electric vehicles. Our customized services include research, testing, training, consulting, and program design. Ronnie and I work mainly on the motors and drives team here at Advanced Energy. Motor-driven systems are estimated to account for approximately 50% of all electricity generated in the world. This is what first attracted to Advanced Energy to motors in the 1980s. And while we continue to work diligently today to make motor-driven systems as energy efficient and reliable as possible. Specifically, in our internationally accredited test lab, we offer independent and unbiased services to governments, original equipment manufacturers, or OEMs, motor manufacturers, variable frequency drive manufacturers, electric utilities, product distributors, motor repair facilities, and various others. I will add that there is a video link on this slide in the presentation that CFE Media will make available to everyone. You won't see it on the screen at this time. That video is from our Advanced Energy Motors and Drives website, which describes our Motors and Drives team in greater detail, and I welcome everyone to watch after the presentation is shared. Anyways, enough about us. Let's get into the meat of the presentation on troubleshooting techniques for AC induction motors. So the presentation itself will be divided into 4 subsections. I will be covering causes of failure and forces acting against motors, and Ronnie will be speaking on test methods and equipment, as well as diagnosing symptoms and solving problems, including various real-world examples. We will start by looking at cause of failure in AC induction motors. We know that electric motors are electromechanical devices housing both electrical and mechanical components. For me, as someone with an electrical background, I'm happy to report the leading cause of failure in electric motors are the mechanical bearings. Really, outside of the structural design, the bearings are the only mechanical element of the motor, so all you mechanical folks need to step it up. According to a study by the Institute of Electrical and Electronics Engineers, or IEEE, as it's more commonly known, over 50% of motor failures stem from bearing issues, as you see on the pie chart. The bearing issues may include lack of lubrication or lack of greasing, using incorrect lubricant, over-greasing, parallel or angular misalignment leading to excessive vibration, overloading, and overheating, just to name a few. Second highest on the list of common failure types will be stator winding issues, which we would characterize as short circuit faults, line to ground faults, or even in some cases open circuit faults. You will notice also on the chart, external or environmental conditions are a leading cause of failure, and we will get into those a little bit deeper here in a few minutes. It's also worth noting on this slide that overheating and overloading are common to many failure types. If you do not take anything else from this presentation, at least my portion of the presentation, please take this: heat kills motors. Overheating will lead to premature motor failure. May not be today, it may not be tomorrow, it may not be in a year, but it's eventually going to lead to your premature failure. It is also very important to understand your application to avoid overloading. Overloading for increased periods of time will, of course, lead to overheating. When a motor is matched to an application, it's typically matched based on nameplate, horsepower, and running speed. In many applications, motor may experience short-term overloads, and due to this, most motors will be marked with a service factor. The service factor can be found on the motor nameplate or in the product literature. Most motors are equipped with a service factor greater than 1.0, which means they can safely operate above rated load. However, always verify nameplate service factor if you suspect overload is occurring. And I think Ronnie will expand on that more later on. Next, we will take a look at various forces acting against the motor during operation. For a motor to perform within design specifications, running temperature must be kept at or below insulation class rating. Applied voltage should be as close to nameplate rating as possible and balanced. Starting torque and rated torque need to meet the load requirements of the application. And mechanical friction within the motor can be overcome during startup. Now we'll expand on those 4 topics. Remember what I said earlier: heat kills motors. Heat is typically the source of primary damage to motor components. Excessive heat may occur from items such as elevated ambient temperature, unbalanced voltage at the mains, blocked or limited fan cooling if there is a fan on that machine, machine overload, vibration from shaft misalignment, and even incorrect motor selection for a specific application. When we talk about heat and motor temperature, you may be wondering how to determine what temperature is appropriate for your motor. The National Electric Manufacturers Association, or NEMA, as well as the International Electrotechnical Commission, or IEC, have standardized operating temperatures. These are defined as insulation classes. Motors will be rated with an insulation class, which applies to the insulation on the windings or electrical wires, but bearings and other components will also be rated at temperatures above this insulation class rating. Looking at NEMA rating specifically, the higher the letter, the hotter the motor can get. In other words, Class H insulation is rated to run at a higher temperature than Class F insulation. Always pay attention to motor-rated ambient temperature. Most motors come standard to operate in a 40 degrees Celsius ambient, and if that is the case, it should say so on the nameplate. Also keep in mind that even though you may have a motor with, for this example, let's say Class F rating, that doesn't imply that you should expect the motor to operate at a temperature of 155 degrees Celsius. Most motors will run much cooler than their insulation class rating, and a general rule of thumb in this industry is that for every 10 degrees Celsius of higher running temperature, your motor winding life will be cut in half. And just in case you haven't caught on yet, heat kills motors. So secondly, along with temperature, voltage is another force acting on the motor during operation. Always verify rated voltage on the motor nameplate. Sometimes you may have multiple voltages on the motor nameplate. Looking from personal experience, I can think back to an instance where a dual voltage rated motor was connected to a 480 volt supply, but was wired for 230 volt operation. All I can say, and keep in mind we're based in Raleigh. There was enough smoke that day to cook a pork butt, and the motor showed core losses well beyond allowable levels for a rewind after failure finally occurred. So a big no-no. It is also worth noting here that most low voltage motors are typically rated at 460 volt, but grid voltage coming from the power provider may be 480 volt. The 460 volt rating is taking into account a voltage drop in the transmission lines coming from the nearest substation or distribution transformer. We have actually completed testing in our lab here at Advanced Energy, verifying that a slight increase in supply voltage above rated nameplate voltage will actually lead to increased motor efficiency. So that testing showed that on multiple 460 volt rated machines, that those machines operated most efficiently at approximately 1.05 per unit voltage, or 483 volts. Once you went past 483 volts, then the efficiency started to degrade. The same testing showed that lower voltages, less than the nameplate voltage, are detrimental to motor efficiency. According to the Electrical Apparatus Service Association's Electrical Engineering Handbook, if we look at a 10% voltage drop from nameplate, motor design torque would be reduced by approximately 20%. In general, if a lower voltage is supplied to the motor would need to draw more current to output the necessary torque and speed for the application. Higher current draw will lead to overheating and motor failure. And don't worry, I'm not going to say that heat kills motors here, but just know I am thinking it. So continuing to look at voltage, we talked about over voltage and under voltage. Another issue is voltage imbalance. So I've completed a couple of metering and verification projects in my time where we have definitely witnessed voltage imbalance in many different plant settings and varying levels of voltage imbalance. I will add that I have a good personal friend that works in power quality for an investor-owned utility, and when we grill out, he insists that their three-phase supply voltage is always well balanced. Now, I'm not going to take any sides, but I will add that most utilities may be allowed to supply certain levels of unbalanced voltage. The point to be made here, and the point to take away, is that even minor voltage imbalance can lead to horsepower derating for your motor. You'll see the chart shown on the slide from NEMA, the National Electric Manufacturers Association, Motors and Generators 1, or NEMA MG1, which I refer to as the Motor Bible, which shows that voltage imbalance exceeding 1% can lead to derating and excess heat. Keep in mind that voltage imbalance directly leads to current imbalance. An industry rule of thumb is that for every 1% voltage imbalance, a motor will show an 8% current imbalance. High current imbalance is, of course, detrimental to motor operating conditions. When you have high current imbalance, you're going to have higher currents on individual phases. When I say higher, I mean above nameplate rated current. And the higher currents on the individual phases can lead to hot spots in the motor windings and, again, to early failure. It is worth noting that voltage imbalance is not the only cause of current imbalance. Unbalanced winding resistance can also lead to current imbalance. So if you are measuring current imbalance with your ampere meter, whether your motor is loaded or unloaded, you may want to de-energize your motor and measure each phase-to-phase winding resistance if you're, while you're troubleshooting. And Ronnie's going to get into that more here in a second. So moving on from voltage, the third force acting on the motor that we'll take a look at is torque. Some initial considerations include, does the motor design type match starting and rated torque requirements of the application? Does the load vary over time? And could the load exceed rated torque requirements? And finally, are the effects of heat derating motor performance? So similar to insulation class rating, NEMA and IEC have standardized how we reference the starting current, torque design, and speed or slip of electric motors, those three factors: starting current, torque, and speed. There are many NEMA and IEC design codes, and we're not going to get into the whole alphabet today. We're only going to cover the most common. NEMA Design B and the equivalent IEC Design N are the most used motors in the industry and are commonly thought of as current limited, low slip, general purpose motors, as it states on the slide. NEMA Design A is similar to NEMA Design B, but NEMA Design A has no starting or lock rotor current limitation. NEMA Design C and equivalently IEC Design H motors are considered moderate slip, high torque machines with current limitations. And then, of course, NEMA Design D motors, similar to NEMA Design C, but with no starting current limitation. To look at a few application types, NEMA Design A and B motors would be used in centrifugal applications like blowers, fans, pumps, or general industry process use. NEMA Design C and D motors would be used in high starting torque applications such as crushers, conveyors, compressors, elevators. It is worth noting that NEMA Design D is the only one of the four standard design types that is not regulated by the Department of Energy to motor efficiency requirements. NEMA Designs A, B, and C are regulated and must list the nominal efficiency on the motor nameplate. So the fourth and final force acting against the motor that we're going to cover at this time is mechanical friction. So mechanical friction is directly dependent on motor bearings. A good place to start is with the motor alignment to the load. Any parallel or angular misalignment can lead to many problems over time, but is especially critical to controlling vibration and mechanical wear. All manufacturing tolerances must be met, including shaft run out, bearing housing, bearing fit, and rotor balancing, among others. Correct bearings must be used for the application. For instance, standard ball bearings would be used for direct coupled loads or lower torque belted or shiv loads. Roller bearings would be more appropriate for belted applications with higher radial loads. And then thinking about even vertical motors, consider whether you have axial force that is upward, downward, or balanced both ways to determine if you may need the thrust bearing on one end of the motor, and that would be most commonly matched with a guide bearing on the other end. And just to reiterate, kind of where we started, bearings are the number one cause of motor failure, so it is very important to follow preventative maintenance routines with your bearings, such as periodic lubrication and vibration analysis. Even when greasing the bearings, verify that proper lubricant is being used and the proper amount of lubricant is being added. Bearings should be maintenance based on run hours. Product literature from the bearing manufacturer specific to your product can give details on lubrication type, interval, and amount. So now that we understand causes of motor failure and forces that act against the motors, well, assuming everyone is still awake and I did a good enough job, I'm going to go ahead and turn the presentation over to Mr. Ronnie Alford, who will explore various problems to look for when troubleshooting and proper tools to use.
All right, thanks, Mike. Now that you all have a basic understanding of where motors fail and the forces acting against them, let's look at what problems we may encounter when troubleshooting motors and what tools we may use in the process. One key factor that plays a part in troubleshooting motors is knowing the motor data and the motor's history. When we talk about motor history, we're talking about how long the motor has been in service and how much runtime the motor has encountered. When troubleshooting motors, if you think the motor failed prematurely, then not only do we want to look at the in-service time, but it's also a good idea to know how long the motor was out of service before running. This meaning, was the motor a spare that had been sitting on a shelf for a period of time before it was installed, or does the system have multiple motors that are used for the same process? There are many cases where motors will sit for months on end where there's no controlled environment and the motor shaft is never rotated. This can lead to many premature failures, such as flat spots on bearings or moisture buildup on the windings. Therefore, this makes this an important part of the troubleshooting process. When talking about motor data, we also want to confirm that the motor in service is appropriate for the application by verifying its mechanical and electrical characteristics are correct. We can accomplish this by first collecting data from the motor's nameplate. Here I've given an example of a nameplate that you would see on a typical AC induction motor. As you can see, there's a lot of information and many different details that can be used during troubleshooting, if we understand exactly what we're looking at. With this being said, let's look at a few of the items on the motor nameplate and what they mean. First, we will see that there is a specific model and serial number tied to each motor. This information can be very helpful when you get to the point of having to replace the motor and you want to make sure the new motor has the same characteristics as the previous motor in service. But we do want to make sure that the motor we are ordering is the correct motor for the application. So make sure that the application information is also passed along to your motor supplier. I've seen many times in the past where a motor matched the basic nameplate data, such as horsepower, RPM, and voltage, and therefore it was installed in the place of a motor that was built for a specific application. A good example of this would be a kiln duty motor that can withstand much higher temperatures, or a washdown duty motor that can withstand direct water contact. There are many motors built for a specific application and therefore makes it just as important as the motor information. Next, you will see the output rating, which is listed here as HP for horsepower or kW for kilowatts. You will see the speed, which is normally notated as RPM, meaning revolutions per minute. The speed can become important if you're troubleshooting a problem when you feel like the motor has slowed down or if you're looking into vibration analysis. Voltage is always an important item to document to make sure the proper line voltage has been applied to the motor. Many motors will give you the option of wiring the motor for different line voltages, such as 460 volt, 230 volt, or 208 volt, so it is always important to check that the motor has been connected with the proper line voltage rating. The current rating can play a big role when troubleshooting a motor that may be giving you specific faults to current draw issues. The current can be notated on the nameplate in a few different ways. Here, FLA is a popular abbreviation which stands for full load amps, meaning current draw at rated horsepower at a given line voltage. If your motor is on an application where the torque fluctuates, it is always a good idea to have a motor with a higher service factor. This will allow the motor to withstand a period of time where the motor can be overloaded by the service factor multiplier. This meaning, if the motor has a service factor of 1.25, the motor can run at 125% of rated load. While keeping in mind that overloading factors lead to higher currents, which in turn leads to higher motor temperature. Always monitor the motor temperature closely to eliminate any chance of shortening the life of the motor. As Mike talked about earlier, the insulation class indicates maximum allowed internal temperatures a motor should operate at, and these classes are based on a motor designed to operate at a 40 degrees C ambient temperature. Standard class rating for a general purpose NEMA motor is referenced usually as class F. But if you know your application is withstanding ambient temperatures above 40 degrees C on a regular basis and the motor runs at full load most of the time, it is best to order a motor with a Class H insulation. Knowing heat is the leading source of motor failures, it is always best to make sure that proper ventilation and temperature monitoring is always in place. Making sure you have the correct enclosures can play a key part in cooling for the motor. There are many different types of enclosures, such as TEFC, meaning totally enclosed fan cooled, ODP, meaning open drip proof, or TAO, meaning totally enclosed air over, as well as many others. Each motor enclosure can be specific to application and to the environment the motor is located in. Now that we know how to compile the data from the nameplate, we need to troubleshoot or replace our motor. Let's look at a few steps to take when moving forward looking for problems that are occurring with an AC induction motor. I always like to include the importance of safety and how it should always be the first priority of troubleshooting, not only on AC induction motors, but on any piece of rotating apparatus equipment in a facility. When troubleshooting a motor that you are going to have to physically touch any part of the motor application or have to remove any safety guards to troubleshoot, please make sure that proper PPE and lockout-tagout procedures are followed. It is also a good idea to advise all appropriate personnel of the inspection. You do not want anyone to not be aware of what is going on and accidentally put your safety in jeopardy. Because at the end of the day, our main goal is to be able to all go home to our families without any injuries. Now that the first key step has taken place and all proper procedures have been followed, we can move into looking at a few basic mechanical inspections. When performing any kind of troubleshooting, do not get ahead of yourself in the thinking process. Always look for the obvious signs first. Some simple but important things to look for when performing a mechanical inspection would be looking for hot spots on the motor frame, such as discoloration of paint. If a motor has withstood enough heat to show signs of external hot spot, it gives us a good idea of the degradation the components inside the motor have seen. We would look for leaking lubricants under and around the motor. Leaking lubricants can play a big role in understanding if the motor bearing grease is getting too hot or if the motor bearings are not getting enough lubricant due to the leak. Broken or missing parts is always an easy but effective inspection. Broken or missing external fan blades can play a vital part of troubleshooting the motor with accelerated temperatures or even high vibration due to unbalanced factors. We can look inside the motor J-box or terminal box for any signs of arcing. As we touched on earlier about motor enclosures, it is always good practice to look for blocked airflow paths. For example, on a TEFC motor, totally enclosed fan cooled, there are a lot of applications that can cause the fan cover vents to get blocked from the materials in the environment. For example, damp paper, damp sawdust particles, rock dust, concrete, or even metal slag. There are so many different contaminants that can produce cooling problems, but sometimes it is just the basic human errors of leaving a box too close to a motor or adding components to a motor to help with contamination buildup, but not allowing enough room for air to flow properly. Once the basic visual inspection has been performed, move on to check for rotation of the shaft by hand. Is the machine free to rotate? If you cannot rotate the motor shaft when coupled to the driven machine, uncouple the motor and check for free rotation of the motor shaft. While doing so, listen for any noise that may be coming from the rotating parts. A lot of times, it is easier to hear or even feel a bad bearing or rotor dragging inside a stator. In some cases, you're expecting a mechanical issue before it becomes a failure. You notice high vibration coming from the motor, but not very clear on where the source is coming from. In this case, you can perform vibration analysis. Vibration analysis is the most common mechanical test for preventive or predictive maintenance. This test is performed by using an FFT spectrum analyzer and using an accelerometer that is usually placed in the horizontal and vertical planes of both bearings and axially on at least one of the bearing housings. There are standards that apply to the acceptable limits of vibration, but make note that the standards such as NEMA state that acceptable limits apply only to uncoupled motors. NEMA acceptable limit is 0.15 inches per second peak for resilient mount motors and 0.12 inches per second peak for rigid mount motors. To help clarify, the limit is higher for resilient mount motors due to the movement that is allowed by the rubber or other type of isolator used during mounting. This is normally seen in smaller motors, such as on a fan or blower application. I recommend always taking vibration readings of the motor coupled to the driven equipment first, for this can help pick up any signs of misalignment, coupling wear, or even unbalance of driven equipment. Now that we have looked at a few different types of mechanical test methods in troubleshooting AC induction motors, let's take a look at a few things to focus on during the electrical inspection portion. Just as a reminder, troubleshooting process start with a basic task and work your way to the more in-depth testing processes. First, we should know that it is best for these tests to be performed by someone who has been trained in electrical testing. By using a voltmeter, we would first check for applied line voltage at the power supply of the motor at each line to ground to eliminate any potential blown fuses. And then we could proceed to test each phase line to line. The applied voltage could be direct wired from a simple on-off switch, or it could be coming from somewhere a little more complex, such as a VFD or soft starter. When performing these tests from a control circuit such as a VFD, we'll want to make sure that the power is available at the incoming and outgoing side of the unit when in run mode. Another useful test to perform when troubleshooting a motor with an electrical fault is the ground wall and continuity test. Make sure if your motor is powered by a VFD or soft starter that you disconnect the motor leads from this device before beginning these tests. The continuity test can be performed with an ohm meter and should be tested from the leads coming directly from the start switch or VFD. By doing this, you can eliminate any possible broken power cables that are running in conduit or underground. If the continuity test fails, disconnect the incoming power cable at the motor and perform the test again between each phase of the motor to pinpoint if the failure is in the motor or in the power cables. If no cause of failure has been determined at this time, we can move on to performing an insulation resistance test that checks for any ground faults in the ground wall insulation. This test can be performed by using a megohm meter, also known in the industry as a megger. You will see in the upcoming exercise how this test can be beneficial. Here we're looking at an example of a 460 volt AC induction motor that will not start. Once we go through the preliminary test that we covered earlier on testing for supply voltage at all three phases and eliminating any blown fuses, we move to the next system component. The control circuit is tested to make sure proper supply voltage is coming out of the unit. If a fault is coming from the VFD or soft starter, use the codes given to help troubleshoot the problem. If a grounded motor is suspect, this can be tested by performing the insulation resistance test, also known as megger test. With this test, the megger or megohm meter applies 500 volts DC to the motor and measures the resistance of the insulation to ground. The applied DC voltage is why it is important to remove the motor leads from any control circuit. The recommended minimum insulation resistance value at 40 degrees C for most motors with random wound stator coils with DC voltage applied for 1 minute is 5 megohms. Low readings may indicate reduced insulation conditions caused by contamination or deterioration from excessive heat over a period of time. If the motor tests at 0 megohms, then it's given the motor winding circuit is grounded and the motor will need to be repaired or replaced. Please note that a megohm meter cannot determine if a complete motor winding circuit is good, as well as determine any turn-to-turn or phase-to-phase faults. These tests will need to be performed by more advanced motor circuit testers. So we have learned from all the considerations that we have looked at today to perform tests and make observations. Understand the operating parameters and remove system components until you isolate the problem. You will see that I've listed a few of the standards that we have referenced today, along with a few additionals. The IEEE 112 standard for test procedures of polyphase induction motors and generators, the NEMA MG1 standard for motor and generators, and the ESA AR100 standard for recommended practices for the repair of rotating electrical apparatus are all great references to use when troubleshooting AC induction motors and looking for specific guidelines. On behalf of Advanced Energy, Michael and myself, we would like to thank you for allowing us to present this topic to you today. And at this time, I will pass it over to Kevin for our Q&A session.
Well, thanks, Ronnie and Michael. As you say, it's time for the Q&A. I'd like to remind our audience that now is your chance to send questions to our panel members, and we encourage you to do so. We already have a good number of questions, so let's get right to it. Michael, what typically causes an imbalance of current in a motor?
Yeah, thanks, Kevin. So we spoke to that a little bit earlier. You know, if you're looking at a couple of different things, voltage unbalance will certainly lead to current unbalance. And we spoke to the general rule of thumb for each 1% that you may see a voltage unbalance, you're going to see 6 to 10% of current unbalance. There are various other factors. The other one I want to point out is winding resistance. If you do have some imbalance in your winding resistance, this will also lead to current unbalance during operation. And obviously, current unbalance is not something that you want because you will see, higher current draw on one of your phases or two of your three phases. It's going to lead to hot spots and premature motor failure.
Well, thanks, Michael. Ronnie, when it comes to electrical surge testing or Baker test, when is it needed compared to regular high-pod?
Yes, Kevin. I would say a surge test is a recommended test along with others when testing the full integrity of a motor winding. Surge tests can definitely help determine turn-to-turn faults, such as shorts between each turn of wire, and can also point out beginning stages of partial discharge. Where a high-pot test, short for a high potential test, which is a dielectric withstand test, uses a high voltage to test all insulation of the motor in or around the winding, making sure no current is passing from one point to the next. Therefore, make sure we have good isolation of the complete winding circuit. I would also note that when talking about high-pot testing the motor in service, to make sure proper voltage testing settings are being used. You do not want to apply the same amount of voltage to a motor in service as you would for a motor that's been reconditioned or rewound.
Well, thanks, Ronnie. Michael, a question for you. What are the effects of harmonic distortion on AC motors?
Yeah, I think Ronnie was going to take that question.
I'm sorry, say again?
The question is, what are the effects of harmonic distortion on AC motors?
Okay. I would say the largest effect of harmonic distortion on inverter duty motors is in the bearings. The bearings are affected by electrical discharge machining, also known as frosting or fluting, that is created in the bearing from voltages on the motor shaft, trying to find the closest path to ground. This could be mitigated with shaft grounding brushes and insulated bearings on the motor, as well as harmonic mitigation devices at the VFD, such as line reactors, DC choke, or a load reactor, near the motor itself, if the lead wires between the motor and the VFD are very long. There are various commercially available active front-end VFDs these days that could provide current THD levels as low as 5%. These have a higher cost, but may be worth it depending on the application.
Well, thanks, Ronnie. I think this next question is for you, Ronnie, but I may be misinformed. Let me ask it of you initially. Can any three-phase motor be connected to a variable speed drive?
I can speak on this, as well as Mike may want to add some to it. I'll say for the motor to run as designed, it's best that the motor be inverter duty rated. This is to make sure that the motor is protected when running at different speeds for the cooling process, as well as that the wire inside the motor is inverter grade rated to withstand the higher voltage spikes. Mike, would you like to add anything to that?
Yeah, I mean, so you're gonna see on a non-inverter duty motor, your wire insulation is going to be different. As Ronnie said, you've got your higher voltage spikes that are produced by your PWM, pulse width modulated signal of your variable frequency drive. And then keep in mind, inverter duty motors will typically show 2 additional ratings on the nameplate further from what we've already discussed. And those 2 ratings will be constant torque and variable torque turndown ratios. The turndown ratios kind of define maybe a safe operating condition for the motor without overheating the winding insulation above that NEMA or IEC insulation class rating. So think about maybe a quick example to go deeper into the turndown ratio. A quarry application, crusher duty motor, if you have a 4-pole motor, base speed 1800 revolution per minute, RPM, you may find, from design specs, you may need full load rated torque down to, say, 300 RPM during operation. In this case, you need to specify inverter duty motor for the crusher that has at least a 6-to-1 constant torque turn down ratio.
Thanks, Michael. The previous questions came in prior to the webcast, so we had a chance to look at them beforehand. These next questions are coming in real time. I'll ask them of both of you. Whoever wants to tackle it first, feel free to do so. And if the question is not appropriate to the topic of this webinar, I would just simply say that that's the case. The first question is, can you discuss the pros and cons of the practice of lubricating motor bearings using an ultrasonic listening device?
That's Ronnie. I can touch on a little bit. I have a little bit of experience of using ultrasonic while lubricating bearings. It is definitely a tool that can be used versus going into the field blind or into a plant with a grease gun blind. The ultrasonic allows you to know when you have installed enough grease into the motor bearing without actually over-greasing bearings. One of the leading causes of bearing failures due to lubrication is actually most of the time not because of lack of lubrication, but due to over-lubrication causing heat within the bearing and the motor itself.
Thanks, Ronnie. Next question. Is the motor voltage changing with a variable speed drive? How is line voltage imbalance affecting motors driven by variable speed drives?
Yeah, and I would like to take that one. So with a VFD, the control strategy typically would be to send a lower voltage to the motor as you're trying to spin the motor at a lower speed. So it's called volts-hertz ratio. And this is kind of basic operation for variable frequency drive. So one of the benefits of a variable frequency drive is that incoming line voltage, issues that you may have on the supply side shouldn't have any impact on the motor. Now, if you're starting to talk about a 10% unbalance or really out there situations, it may make it through, or else the variable frequency drive is going to trip out. But thinking about the way the VFD works, the VFD takes in AC voltage, converts to DC, stores it on a bus, and then converts back to pulse width modulated signal that it's sending to the motor. So really, the voltage that the drive is seeing on the input is much different than what's being seen at the motor. So a voltage unbalance condition at the drive shouldn't have much of an impact to the motor.
Thanks, Michael. I suspect this next question is for you, Michael, as well. Can you give us any guidance on when shielded cable power leads should be used for a VFD application?
Yeah, that's an easy one, always. There are cost considerations, and that's maybe why you wouldn't look at this in a lot of situations, but every VFD manufacturer is going to tell you always use your shielded power leads.
Good, thank you.
VFD cables.
Ronnie, a question for you. We talked a lot in this webinar about the danger of overheating a motor. How do you determine that a motor is overheating?
Yes, Kevin. As you spoke, we've talked a lot on this because of the importance of heat with an electric motor. There's a few different ways of determining if a motor is overheating. The best recommended, I would say, in motors in a plant is to have internal thermocouples installed in your motor during the repair or purchasing process. This way you can attach it to your control circuit and you're always seeing real-time temperature monitoring. If that's not the case, then I would definitely invest in thermography cameras, infrared cameras, and at least go out once a month and take some baseline temperature readings of your motor at the rated load of where the motor runs most of the time, and then just trend that value.
Great, thank you. Michael, a question for you. What happens if you run a 50 hertz motor on 60 hertz?
Yeah, and this, it's a good question because, and we see this kind of stuff all the time. Looking at NEMA is going to be specs typically, American frame sizes and horsepower ratings, and then at IEC you're going to have the more European style frame sizes, metric system, frame ratings. So in Europe and other countries outside of the U.S., you're running on a 50 hertz power supply. And so the motors, 50 hertz motors really aren't rated to operate at 60 hertz. They may for a while, but what you experience is saturation. And so the machine, it's not going to operate for long, and even if it does operate, the torque output is going to be reduced by 5/6, 17%. So, recommended not to do that.
Thanks, Michael. Michael, another question for you. Do you feel 500 volts is a proper level of voltage when testing motors used on VFDs?
And the question, I'm not sure I'm getting the feel of the question, but what I wanted to speak to is when you're running motors with VFDs, some VFD manufacturers may say, hey, if you're feeding, say, 460 volts into the VFD, and then the motor's is rated to run at 460 volts, they may say, hey, you're voltage starving my machine, so it's not able to get enough voltage to the motor. So I think that's what this question is getting at. If you have, 460 volt output, there's nothing that's going to be stopping you if your variable frequency drive is rated for up to 480 volts or 500 volts. Nothing stopping you from applying that on the supply side, and then the VFD is going to regulate what your motor is seeing. So I hope that answers the question. If there are further question on that, feel free to reach us offline.
Thanks, Michael. Ronnie, a question for you. How long can a motor run at its stated SF?
That's a great question. I know we talked about it a little during the presentation. There's many different terms we've heard in the past of the service factor should only be run for a short amount of time, or that time has no value of how long it can be ran at that service factor. Like I said during the presentation, the best way to go about monitoring that is to keep up with the motor temperature. The motor may be rated at 1.25 service factor, so you're running at that 125% load. But I would say as far as amount of time, it's going to depend on how much hotter the motor is getting due to the overload and the high currents.
Great. Thanks so much, Ronnie. That's really all the time we have for questions today. I'd like to thank our panelists, Michael and Ronnie, for participating in today's event, and I'd like to thank our listeners for attending today's webcast and asking questions. We hope it suited your purposes. For more information, go to the website links noted in the interface. In closing, I'd like to thank our sponsors for today's webcast, and now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it as we use this information to improve our webcast. On behalf of CFE Media and Technology, we'll see you next time.